Hello, everyone. Welcome back to Historical Geology 1404 for the last time. This is our last lecture. You are getting the last little bit of your content that you need to complete things like Lab 5, to do your lab exam, which will open today. And because we had Thanksgiving on a class day this semester, you are also getting your final exam today. So both exams will open today, and both will close Thursday at midnight. Okay, so you have all day for Thursday, and I have a close so that I can come in on Friday morning and calculate final grades before I have to walk across the street to graduation. Okay? All right. Let's see. We'll just go over the content for now, the lecture 13 content, and then we'll have a little bit of information, a little bit of information session for the lab exam. And then we'll move on to our review for final exam. Sound good? Before we begin, any questions or comments? We had a pretty sizable earthquake in California this weekend. Actually, it was on Friday, I believe. 7.0 in Northern California, pretty big. Those are uncommon. I won't say that they are rare. They are uncommon to be that size. They get 4s and 5s all the time. We don't even talk about that. Matter of fact, I learned about this earthquake 2 minutes after it happened because I'm connected to the U.S. Geological Survey seismograph network. I get reports sent directly to my phone at the same time that the USGS gets them. So I got an alert about this almost immediately. But I turned off all alerts for anything below like a 5.5 in California because they get those all the time. They have so many faults over there, right? I think that was the only, oh, no, there was a volcanic eruption in the Philippines as well. Pretty cool. Actually, as a matter of fact, let me, Are you talking about in Tonga? Yeah.
See, I didn't get confused.
Yeah, then it was pretty devastating for the nation of Tonga. Okay, so this is on X, so hopefully there's nothing sketchy on here. Come on, let's start this over. Watch the shockwave go through the clouds. Did you see that? Yeah. Okay, I'm going to make this bigger, and then we're going to start it over. Watch the shockwave go through the clouds. You see that? Pretty cool. So yeah, this volcano is erupting in the Philippines right now. They've evacuated the area around it. You see the pyroclastic flow going down the side there? Okay. Other than that, I can't think of anything of note to discuss. Any questions about that or anything y'all want to bring to the table? No? You what? I still couldn't hear what you said, brother.
It's a shark that lives in the volcano.
A shark that lives in a volcano.
The shark that Lydia was talking about.
Yeah, the Tongan volcano. What about it?
See, they know like you said sharks. You say sharks are living or living under.
Oh, yeah. That volcano, a big part of it was underwater. It was one of those atolls that we've talked about. Coral reef grew up around it. It's one of the volcanoes, estimated about 2 million underwater volcanoes that we simply can't keep track of. There's far too many of them for us to watch and monitor, which means that when they erupt, it's often a surprise and it catches people off guard and there's damage as a result, like what happened to Tonga. But were there certain species of organisms that probably lived in it as a habitat? Most definitely. As a matter of fact, since we're on the subject of species under threat from such activities, that earthquake in North California a few days ago, its seismic waves traveled through North America and interacted with an ecosystem on the border between California and Nevada. There is a cave there Oh, here's Mr. Hart talking about caves again. Right. That has a species of fish called pupfish. It's the only location that we know of that they still live naturally. Okay, in this one cave filled with water. They are protected, they're endangered. We do everything we can to take care of them, but there is nothing that people could do to stop the seismic waves. So the seismic waves went into the cave and sent like 2-foot waves through the water in the cave. Severely disturbed the ecosystem of the pupfish, destroyed most of their eggs, and sent most of the decaying vegetation that they eat for food too deep in the cave for them to get to. So now the species of fish that is endangered and only lives in this one habitat is in critical danger of dying out here in the next little bit because of this natural circumstance. Classic example of how nature can wipe something out, right? It's not always us. But yeah, and they're scrambling to try and figure out what we can do to save these pupfish. You have a comment?
Yeah, so apparently these pupfish, they're like hated by big corporations because they can't mine on the land.
Yeah.
Just because they're there.
Well, pupfish, quail, certain species of turtles and salamanders, all birds that nest on the ground, all of these are organisms that do stop mining and oil field operations because they exist in a certain area. The gold mine that I worked at, we were exploring a brand new area that we believed had a lot of gold, and we took samples, and there was a substantial amount of gold there. But there was a big chunk of the area that we had to flag off basically to work around because certain species of bird nest there during parts of the year. And because they are nesting grounds, we couldn't have any operations there. A lot of gold under those nesting grounds, but we had to move around them because they were there already. As a matter of fact, it's federal law that you have to have a state certified biologist walk across all of those areas with you and do a test, do a check, collect data, collect samples, figure out, is this a vital ecosystem for any of the species we know that live in the area? And if they give you a clean bill, then you can operate there. You can drill your oil wells, you can put your wind turbines, you can make a gold mine. But if they say, no, sorry, this area is being used by some aspect of the ecosystem for something that they need, then you can't do anything about it, which is good. I think that's good practice. There's plenty of other places we can dig without needing to, destroy nesting grounds or something like that. Good conversation topic. All right, well, let's jump into the Paleogene. Where did we leave off? The end of the Mesozoic. What did we lose in the Mesozoic? Dinosaurs and a few other things, right? The Paleogene picks up at 66 million years and ends 23 million years ago. We lost our dinosaurs. We lost our flying reptiles. We lost our swimming reptiles. And yes, we lost ammonoids. They stuck around for so long. They couldn't make it through this one, though. So ammonites, just fossils now. However, their nautiloid cousins stuck around, which is fun because as far as the fossil record tells us, nautiloids came first. And they had the last laugh too, because here they are still. Very similar in structure, design, as far as we can tell, to the way that they have been forever. Very similar to the way that they were previously. Ammonoids changed a lot, but couldn't quite make the cut to recover after this extinction event, okay? So also those rudist bivalves that were so screaming successful during the Cretaceous and only lived during the Cretaceous, they show up at the beginning of the Cretaceous and they die at the end of the Cretaceous. Obviously, those are gone too, which is why we use them as index fossils for Cretaceous rock. Now, massive niches left vacant. Dinosaurs and swimming reptiles and flying reptiles filled so many positions in Earth's ecosystem niches, which remember are kind of like those apartment spaces in an apartment building, right? That fulfill some part of the demand of the ecosystem. Those are so many of those are left vacant. What's left is going to
Be occupied.
Yes, it's going to occupy them, but what do we call that? When surviving organisms diversify to fill new niches?
Radiation.
An adaptive radiation. Bingo. Okay, so the surviving organisms radiate. Okay, they diversify, they change, they fill those niches. What before could have been meaningless or even negative characteristics, traits through mutations, are now given an opportunity to become successful in some new niche. For example, mammals. Mammals were big or small during the time of the dinosaurs? Small. Why? Why was that positive? They wouldn't have stayed small for all that time if it hadn't been positive.
Reptiles to hide from them.
If you are a mammal that is born with a mutation to be larger, that's a bigger prey, more likely that you're going to get tracked down and eaten by some reptile, some dinosaur, right? Stay small, stay hidden. That was the name of the game for mammals. Now that the dinosaurs are gone, that same mutation to become larger is no longer a negative. It's now a positive mutation. And as a matter of fact, we see mammals get big fast after this transition, after this extinction. Okay? So now that the game has changed, the rules of the game have changed, these mutations have a whole new context. So our mammals, birds, okay? Birds are going to change quite a bit. Scleractinian corals, which are the type of corals that descended from hexacorals and now dominate our reef systems today. They are made out of scleractinian corals. Those hexacorals that showed up in the Jurassic we talked about, ancestors to these. We'll talk more about that. Okay, so the Paleogene, though, is made out of 3 periods, or epochs, excuse me. The Paleocene, okay, so there's Paleogene and Paleocene, and then the Eocene and Oligocene. The arrangement of mammal-dominated interactions that we see in our biosphere today. Pretty much anywhere you go, even a lot of things in the ocean, a lot of situations in the ocean, although less now because of certain actions that have happened, tend to be dominated or have some form of a mammal near the top of the food chain. On land, obviously, there's a lot of us, right? I have a cool graphic that if you remind me later, I can show y'all. That shows the Earth's biomass by quantity. Spoilers, humanity makes up a lot of Earth's animal biomass, but we'll talk more about that later if you remind me, okay? But mammals really quickly start to take the top dog positions in these ecosystems. They had some competition right off the bat, okay? Birds in particular. Reptiles never really recovered fast enough to be much of a threat to early mammals. Mammals were just able to adapt much faster. But birds, yeah, there were some big birds that did their best to fill those niches before mammals could. And in the end, they lost, obviously, because here we are. We aren't a classroom full of birds, right? We're a classroom full of mammals. Eventually, they kind of took those positions, okay? But very shortly after this extinction, we see big mammals, we see a wide diversity of mammals, thriving ecosystems, something that would have looked something like this. This doesn't look terribly dissimilar to ecosystems we have today, okay? Rhino-like creatures, horse-like creatures, giant hunting cats, right? Only 3 species of planktonic foraminiferans survived the Cretaceous extinction. Only 3 species out of the hundreds that existed in the Cretaceous soup. You remember I told you how many little things were living in that ocean water during that time? Made those massively thick chalk deposits, right? That's out of all the stuff that lived in that soup, only 3 species of forams survived. And from those 3 species, diversified all the ones we have in the ocean today. Came this close, right? Cretaceous was bad for them. Early on in the Paleogene, reefs weren't really a thing. And we think it's because of the chemical change that occurred in the ocean as a result of both the temperature change from the mini ice age that happened, but also input into the oceans from all the ash could have changed ocean chemistry just enough to make it slightly more aragonitic calcite. So if that was the case, some species of coral don't really do well with that. They dissolve easier, they break easier. Reef systems can't get as big because once you get enough weight, they crumble and fall apart because it's made out of an aragonite coral instead. There's another very distinct possibility here. There exists in many species of coral that we have today a symbiotic relationship with a type of algae, bacterial colony. We have this as well. Did you know that? How many of you know that you have a bacterial colony that lives in your gut? Yeah. As a matter of fact, a lot of it are archaean organisms, okay? Do you remember early on when we talked about the beginning of life, how there were archaeans and there were bacteria, and archaeans kind of came before bacteria? Archaeans are mostly extinct in the world around us, but they exist. One of the most common places to find them is in your stomach. We've had that symbiotic relationship with them for a very long time. Our ancestors a long time ago, their ancestors a long time before that, and it lives inside of us, okay? Nature kind of picks these patterns. I'm going to go on a little tangent here. I hope you all bear with me here, okay? Nature loves stuff that works. So early on, you'll see wide diversity of things, especially after an extinction, but then bit by bit, things will die off, and the things that work will survive. And then those things, there will be a massive diversity of those. So early on in Earth history, we see huge variety of crazy-looking organisms in the Ediacaran fauna and all of that. But then we start to see patterns, symmetry, and then radial symmetry, and then limbs exhibiting that radial symmetry. Think about all the things that we have in common with every other animal on Earth. We have radial symmetry. Head, 2 arms, 1 on each side, approximately equal to each other, right? 2 legs, 1 on each side, approximately equal to each other. Radial symmetry. Manifested in me. Manifested in a starfish. Manifested in a jellyfish. Manifested in a salamander. Manifested in an orangutan. Radial symmetry. Manifested in a fly, on a cockroach. And then internal digestive systems, like tubular digestive systems. We have intestines in all of these organs. So does a cockroach. So does a bat. So does a lizard. So does a frog. So does a fish. All of these things are patterns that worked and they stayed. Right? It's funny to me. It's very interesting to me to watch how nature loves diversity, but then once something that works is found, it just is variations on that theme. I don't look like an orangutan, but there are definitely similarities, right? I don't look like a bat, but there are definitely similarities. I don't look like a fish, but there are definitely similarities. Variations on a theme once that theme is found to work. That's how it tends to play out. I just wanted to point that out. All right. So this symbiotic relationship, very similar to what you and I have in common with our colony of archaean and bacteria in our guts. The same thing corals have, the same symbiotic relationship. This colony of algae that they contain within them, these corals, helps them to digest and process the food that they capture. So the algae gets to keep that energy, while the coral gets to process food faster and more efficiently. Symbiosis, right? So we believe what may have happened was the chemical and temperature change as a result of the Cretaceous extinction may not have killed the coral, because we still had coral, but it did, we believe, kill off that algae that they had that symbiotic relationship with. And the reason why it took a little while for these coral reef systems to redevelop is because a new symbiotic process had to be found. New archaean, a new, probably not archaean for them, but probably new bacterial colonies, a new symbiotic relationship had to be formed. And so once that was established, once a mutation allowed these to bond to each other and have this symbiotic relationship, then corals started coming back and making those big coral reefs. Okay, a couple of factors at play here. With the loss of our giant swimming reptiles, that niche was left vacant and got filled by two organisms. Sharks, which I'm sure all of you, thanks to a certain set of movies starring Jason Statham, have heard of Megalodon, right? The largest shark that ever lived, as far as we are currently aware. I have several of their teeth right here. This one is my biggest one. This is a replica of a real size of a tooth, but it is a replica. Let's see if I can put it back on there without making it fall. Ayo. All right. And then this is a real one. This is a real megalodon tooth. This thing's got big, 40 to 50 feet long. Possibly, based on the size of some of the teeth that have been found, there's the potential they could have gotten as much as 60 feet, depending on how long they lived, where they lived, how much they were able to eat, etc. Really, really, really big. I'm going to pass that around. Please be careful with it. This is the size of a megalodon set of jaws in comparison to a great white shark that we have today. They're actually cousins to each other. They belong in the same genus. Great white shark, Carcharodon carcharias is the genus and species. Carcharodon megalodon. So close, in fact, that basically whenever we want to portray an image of a megalodon, you just take a great white shark and blow it up. As far as we can tell, very, very similar to each other. Only difference is body size seems to be the largest difference between each other, and that's why they are different species. Megalodons have been extinct for quite a while. I know several people who would contend otherwise. They're like, but how do we know though? Well, because the youngest tooth that we have is like 12 million years old. We haven't found anything younger than that.
How did it crystallize?
Same fossilization process as everything else. One of my life goals actually is I've been to North Carolina a few times, but I want to go back to North Carolina and scuba dive off the coast to find my own megalodon teeth. That's where you find them usually, is scuba divers digging through the sediment off the coastal shelf in that area. All right, that's sharks. But then there's the whales. Now, whales have a very, very interesting history, which we will talk a little bit more about later. But for now, whales are not, and during this time, the way that you think of whales now. When I say whale, what do you think? Save the whales. They're just giant, helpless, sweet little animals. Well, that's true. They are, for the most part, large, sweet, gentle animals. But now imagine an orca. Orcas are jerks. Now, I know that's probably going to be an unpopular take for whale lovers out there, but if you've never seen an orca play with its food before finally killing it, then you don't really know what you're talking about. Okay? Orcas, just like other whales, have definitely been victimized. I'm not going to go into the whole SeaWorld debate here, but orcas out in the wild are vicious. They demonstrate the ability to be cruel. They're highly intelligent. They belong to the same group that dolphins do, the same group of whales that dolphins do. Large brain capacity, ability to feel pain, pleasure, and apparently cruelty. Because there's no other way to describe some of the things that orcas do. Sperm whales Also, very large whale predators. Okay, if you've ever heard of Moby Dick, large whale predator, right? Dolphins themselves, whale predators, actively hunting down their prey. Now imagine an orca or something as vicious and as refined for the hunt as an orca, but much, much, much larger. Orcas get 16, 20 feet long, I think, tops these days. Imagine 40, 50, 60-foot long whales with giant teeth being the apex predators in the oceans, competing with things like megalodon. Yeah, pretty sketchy. This is kind of a progression through time of whales, going from these small little rat-like animals that we were coming out of the Cretaceous and into the Paleogene, moving out into the water. As a matter of fact, this particular organism right here is something that was only found within the last couple of decades, I believe. I don't remember the exact name, but I don't remember the name of this, but this particular organism, the fossils were found in Pakistan. For the longest time, we could not find the link between small mammals living on land to slightly larger mammals that had moved out into water. And then they found these fossils in Pakistan, which is a very, very nice, neat transition between the two. It's kind of a missing link, if you will. Now, some other organisms branched off from this as well, one of which you are very familiar with. Do you know what the closest relative to whales are? Another descendant that branched off from that stage of evolution.
Dogs.
Huh?
Dogs.
No. The closest living relative to whales are hippos. Yeah, they're actually cousins. Yeah. Not that far off genetically. I mean, okay, they're pretty far off genetically, but they branch from a very recent, geologically speaking, recent common ancestor. Okay? They're the closest relatives to each other in the mammal kingdom, or in the mammal world. Okay. Plants. We have the whole setup for our plants. We have our flowering angiosperms. We still have our gymnosperms. They stuck around. They didn't suffer enough during the extinction that anything changed really. Except that now grasses are becoming more and more common. Grass actually started to develop at the end of the age of the dinosaurs. What did I say filled the same niche that grass does now back then? Ferns. For most of plant history, going from before the dinosaurs to shortly before the dinosaurs died, ferns everywhere. Grasses start to show up in the Cretaceous, towards the end of the Cretaceous, but they don't really look like the grasses we have today. We'll talk more about grass here in a little bit, but we don't actually see true grasslands until pretty much after the dinosaurs are all gone, as far as we can tell. Were they around way before that? Sure, but not so much niche dominating. Okay. So let's look at this, this progression of mammal life through time. All of these things we don't necessarily need to go into. Most of them died off anyway, but the few things that did survive and go to diversify, let's look at these two branches out here. Out here, we can see monotremes, like our platypi and echidnas, marsupials, like kangaroos and wombats and Tasmanian devils and all of those, okay, out here, okay, bless you. Then there's another group out on this side called multituberculates. Multituberculates were the most successful group of mammals during the time of the dinosaurs. There were lots of them, a wide variety. The width of this, you can kind of think of that as being the diversity of species within this group, okay? So many, many, many different groups of multituberculates occupied the space. Very successful during the end of the dinosaurs, and then after the dinosaurs died off, the most successful group of mammals compared to the rest of these, which kind of struggled early on or couldn't compete quite as well with the multituberculates. Multituberculates, you kind of think of them as very large rats. Looked kind of like that. Talk more about multituberculates in a bit. But what do we have here? Okay, all of our major groups start showing up. Okay, modern carnivores like your bobcats and your big tigers. Okay, primates right here. Let's see, whales right there. Rodents. Look at rodents. I want to point this out right now. Notice that at the same time that rodents are kind of struggling and then really start picking up speed through time, lots and lots of more diversity in rodents. What's happening over here to the multituberculates? Yeah, they're declining until they eventually die off. They die off about halfway through the Oligocene, about the same time that things for the rodents really start exponentially getting better. Remember that. That'll be relevant here in a little bit. During the Paleogene, we see the development of the ballpark 100 families of mammals we have today. There have been some more through time, there have been less through time, but it generally fluctuates around the 100 mark. That's about, during the Paleogene is about when that happened. It hasn't changed a whole lot numerically since then. That may change as our current ongoing extinction moves forward, but for now, that's where we sit. During this time, horses were about the size of tabby cats. These are the earliest horses. These were often hunted and eaten by giant flightless birds. It's weird to think about horses being hunted down by birds, but that's the way it was. It took very little time. I mentioned this earlier. It took very little time for mammals to diversify to fill those niches, right? That's naturally what happens after an extinction. Picture this, though. 12 million years. To you and me, very long time. But you know already in our discussions through this class and in 1403, 12 million years is barely even a blink of an eye in geologic time, right? It only took 12 million years after the extinction of the dinosaurs to go from just these rodent-looking animals to having whales in the ocean and bats flying in the sky. That is incredibly fast evolution to have such incredible diversity. Mammals really picked up their game, filled in those niches, no problem. Hoofed organisms appeared during the Paleogene. Now, we still have hoofed organisms, and we break them into two categories, which we call ungulates. Okay? Even-toed ungulates, camels, bison, pigs, anything that has 2 or 4 toes. And then odd-toed ungulates, horses, tapirs, rhinos. Horses have how many toes? 1. They have that 1 hoof, right? Rhinos have 3. If you've ever seen a rhino foot, they've got 3 toes. Okay? Same with tapirs. All right. Elephants show up during this time, but they don't look like our elephants today. This is what elephants would have looked like during the Paleogene. Doesn't look much like an elephant. Looks pretty ugly, actually. But look at these teeth. What do you think this thing ate?
Watermelon?
People. No. Yeah, probably watermelon and stuff like that. No, but these teeth, especially these ones that are kind of shoved out into the front on the bottom jaw, what a weird place to have giant teeth. They would use these to dig through the muck and the mud looking for roots and things. These were herbivores. These teeth were not used for killing and hunting or anything like that. Okay? But you can definitely see some characteristics here of what would eventually become elephants, right? This body shape, expanding ears. These teeth do, in fact, eventually become tusks. As a matter of fact, if we go all the way to the end of the Paleogene, looking down here, this is what they look like. We go from this to that. You can definitely see how this has progressed through time here. These same ears, but they've become longer, floppier. Body size has increased, right? But the body shape has stayed pretty much the same. Those teeth in the front are becoming longer, more tusk-like. This kind of wiggly, tapir-y sort of nose up there has become the beginning of this trunk. You see how this is eventually going to become elephant.
How big was the one on top?
This one, about the size of a tapir, probably about that. Huh? It kind of likes, yeah, it's like if you somehow could cross an elephant with a rat. Yeah. Well, they came from those rat-like organisms, right? This is one of those multi-tuberculates I told you about, like a rat beaver sort of thing, right? Now, multi-tuberculates, wildly successful for a long time. What got them? They were out-evolved. They had many characteristics that gave them great advantages, but rodents and the other group that would eventually branch off and become things like rabbits and hares and all of that, rodents had a big advantage over multi-tuberculates. Multi-tuberculates could not keep growing teeth. Their teeth would grow in and then stop growing. And so if they ate enough stuff and their teeth wore down to the point where they couldn't eat anymore, that individual would die. That was totally fine until rodents showed up on the scene with the evolved trait to continuously grow their teeth. Rats, mice, they all keep growing their teeth. They couldn't care less if they break a tooth or if they wear their teeth down, it'll just grow back. That's why rats are infamous for chewing through concrete and sheet metal. They don't have this innate instinct, stop chewing. They can chew through whatever they really want because it's just natural to them to have more teeth that will come in later. Okay. What advantage does that give? Longer lifespans. You don't die from starvation if you have teeth that you can eat with, right? And so they outcompeted the multi-tuberculates, and these guys were gone before the end of the Paleogene. Ow. All right, the largest land mammal to ever live, Paracitherium. That guy right there, 20 feet tall and 25 feet long. If you had to guess, tell me what modern day mammal is descended from this guy? Giraffe. It's pretty obviously a giraffe, right? Well, you're pretty obviously wrong. Rhinos. Yeah, I know. Rhinos actually are descended from Paracitheriums here. They're the closest relative. Okay. They did change a lot. However, there are definitely some things that you can notice. Their leg structure, for one thing. Their feet, very similar. But also, these kind of armored skin folds around the joints and around the limbs there. Still see those in rhinos today. But yeah, rhinos, these guys. Early on, the largest predators, mammal predators that were on land were what we call mesonychids and creodonts. Mesonychids look like this. And I don't really have a good picture of a creodont, but they're very similar. Okay, very similar, filled similar niches, competed with each other. It is from mesonychids that that organism that would go on to become whales showed up. And it is later on in the Paleogene that we see the development of cats and dogs coming from these organisms, okay? Think of these as the ancestors of both cats and dogs.
So I was right. Dogs are like related to whale.
You're related to a whale. You're welcome. Okay. Birds. Giant flightless birds were one of the biggest competitors with early mammals. Okay. Diatrema, looking like that. We call them terror birds. That bird probably stood about 7 to 8 feet tall. And yes, you are seeing it eat a horse right now. It's eating one of those early horses. There is some evidence that maybe we misjudged these things and they instead ate fruit and nuts. But then there are some other very good, compelling arguments against that. We'll figure it out eventually. But for now, we still consider them to be predators. They were competing with early mammals. Primates. Our first primate shows up about 55 million years ago. That's what he looked like about, okay? Just a tiny little dude. A rat that took to the trees, really, okay? Probably about That big. Yeah, very, very small primate. By the Oligocene, we have what we would actually consider to be monkeys, monkey-like primates. Okay, we'll see the progression of the primate family a little bit more here in a little bit. Okay. All right. Climate-wise, we have a lot more data about these more recent time periods than we do about the older ones. Why? Well, because there's more rock closer to the surface we can access that contains those things, plus the fossils have a better preservation record, and so we can get more paleo-environmental data from them, right? And that's also very relevant to us, a lot more relevant to us, because we can see the more recent patterns in Earth history. There was, between the Paleocene and the Eocene, right here, what we call the Paleocene-Eocene warming event. This is an isotope map, delta 8 oxygen 18 isotope tracker, okay? And here's temperature on the scale, okay? So as temperature increases, the delta oxygen 18 decreases, okay? We approach 0 or go past it based upon a ratio. This is based upon a ratio to delta oxygen 16, okay? So if we go past 0, then that means that the ratio has switched, basically. All right, so here we see okay, oh, okay, well, things are getting a little bit colder, and then it gets warmer, and then whoa, what the heck happened there? That's everywhere. All across the planet, we can see that. Okay, this one spike of temperature for that very short period of time, that's actually why we put that transition right there between the Paleocene and the Eocene. That's why it's there, is because of the spike in temperature. Something happened there. We think what happened was because of some tectonic activity taking the bottom of the deep sea, okay, the bottom of the ocean, and pushing it closer to the surface, millions and millions and millions and millions, I'm talking hundreds of millions of years worth of methane hydrate crystals, which had formed at the bottom of the ocean where it was really cold and they could be kept in their crystal form. Because the bottom of the ocean got pushed closer to the surface into warmer waters, those methane hydrate crystals dissolved, the methane percolated up through the water, released into the atmosphere, and caused a global warming event, a very rapid global warming event. Okay, so temperatures spike, which causes an extinction, and we draw that line there. Okay, now things stayed kind of hot for a while. They actually got pretty warm during the Eocene before and then another spike here, which was probably for the same reason, methane hydrate crystals, but we still continue our general downward trend into the Oligocene. The Oligocene is commonly considered to be an ice age, okay? As a matter of fact, the ice age during the Ice Age movies is supposed to have been during the Oligocene, which is funny because a lot of those animals are from the Oligocene, but men weren't nearly around yet. They kind of, can you believe that the Ice Age movie messes some things up? I know, it's hard to believe. Movies these days. Anyways.
And the continent didn't break because of a nut.
Yeah, the no continental drift, no dinosaurs frozen in ice, no pirate mammals. I'm sorry to break your hearts like this. Okay, so we get our ice age during the Eocene-Oligocene transition, and it stays pretty cold and gets even colder towards the end of the Oligocene. All right, geographically, what are we doing tectonically? Look, we've got what appears to be a very similar situation to our modern arrangement of continents. Pangaea has long since broken up. We have not had another supercontinent since then, right? We're a long ways from another one now. Australia, you can still see Australia from Antarctica on a clear day, probably at the beginning of the Paleogene. But it's moving further north, okay? India has not made contact with Eurasia yet. It is about to, okay? In about 55 million years or so, it hits there. And then Africa, moving north, eventually it's going to run up into there. And what this right here is eventually going to be the Mediterranean Ocean, that patch of this strait. Our Rocky Mountains are still developing over here. South America off on its own. It said goodbye, Africa, but it has not made Central America yet to join with North America. We have the Laramide orogeny, contributing to the formation of the Rocky Mountains right here, okay? So this was a highly volcanic time period over there, okay? Lots of granite plutons are formed during this time, come very close to the surface. There's lots of thrust belts, which remember a thrust fault is a very low angle sort of reverse fault situation where one layer kind of scrapes across another layer instead of getting sliced through. And because of that, it can be very low angle, which means that it can push further across much more distance. And so every time something runs into the west coast of North America, it shoves these thrust faults a little bit further east. And that's what contributes a lot to the formation of our Rocky Mountains. That is the laramide orogeny. The Tejas cratonic sequence occurs at that Paleocene Oligocene, from the Paleocene to the Oligocene. So it stretches over the Eocene, okay? So pretty much during the entire Paleogene. This is when, and if we go back to our previous picture, you can kind of see this. A lot of what is now the Gulf of Mexico is still underwater, and actually it doesn't show this here. It really should. There's actually water that stretches up into North America this way, okay? The entire area of what we currently consider to be the Mississippi River embayment, all the way from what is now Louisiana, all the way up to Memphis, Tennessee, this was all underwater during the Tejas cratonic sequence. All of this area today has a lot of ocean deposit. There's a lot of sand, there's a lot of beach sand that was deposited there, while there was all that shallow ocean that stretched up into North America right there. And this is also when we see the development of the Rio Grande Rift. If that sounds familiar, it's because it's very close to us. Where the Rio Grande River is right now. How many of you have been to the Rio Grande River? Okay, well, I mean, sometimes it's cool and sometimes there's nothing there. But where the river is right now, that river runs right there because there is a rift valley forming there. The same thing that's happening in Eastern Africa, that East African Rift Valley, where it's splitting apart. There's a divergent plate boundary forming there that's splitting that continent apart. At that same location, or excuse me, here at the Rio Grande River, where the Rio Grande River is, there's another rift forming here. Given another 20, 30 million years, there will be an extension of the Gulf of Mexico coming up into North America, where the Rio Grande River is right now, as it continues to split apart and get thinner and deeper, and the ocean can move in. Okay, that started happening here during the Paleogene. And then there was a massive asteroid impact about 36 million years ago that struck where the Chesapeake Bay is right now. The Chesapeake Bay would not have been a bay without this asteroid impact. It would still be where a river delta, where a river runs into the ocean. But instead, we've got a big open bay because this asteroid slammed into it, destroyed a whole bunch of the geography, and now as a result, and the way that this filled in between now and then, we have a bay right there. So this is what a cross-section of Chesapeake Bay looks like. Here's the ocean. There's the bay. You can see where the bay exists now is because sediment, later layers of sediment kind of faulted and fell into this breccia, this asteroid impact breccia, because as this is compacted over time, these layers of rock have compacted down on top of it and faulted in, leaving a low area for our bay to form there. That's the Paleogene. Any questions? No? Okay, well, let's move on to the next one. The Neogene. Uh-oh. Not responding. Don't tell me that. Okay. Now, before we get started on the Neogene, I'm going to be right back.